Hello, dear students. So this is our another lecture on these complex analysis. Because if you remember that in our main focus is to solve the different problems which basically come in different competitive exams on these complex analysis, right? So because our today's topic is it is about that what's basically the branch point and what are basically branch cuts, right, in complex analysis. So if you know that with complex analysis, so we can do mapping from some one complex plane to another complex plane, which is called Movie's transformation. And similarly, if you have some functions, so there may be some functions, some analytic functions which are single valued, which have one value at one point. So, but there are some functions which are multi-valued, right? So suppose if you consider some function, we have some square root of this z, and if it is equal to some number w, right? And if you want to make a transformation from this plane to this one, this complex plane to that plane. So this is our z plane and this is our w plane, right? So this is our complex plane here, and we want to make transformation. We want to do mapping from this z plane to our w plane. Okay. So if you choose now, so that means if we consider some point here, so we are basically saying that the argument of this, that's theta, we consider some point. Okay. So if you want to make transformation, if you rotate this from 0 to 2 pi, so if you rotate from 0 to 2 pi, so it makes complete that rotation. So that means if you put that for this, if you put that, because we know that z equal to that or e power iota theta. So this is basically how you write that complex number in that polar form, because you can write that it is equal to r cos theta plus r iota sin theta, right? Now, if you choose now, if you put now, if z equal to, if z goes from 0 to 2 pi, so if I rotate that, अगर मैं rotate करूँगा from 0 to 2 pi, so that covers this whole that complex plane. But instead of that, so if you want to make that transformation, if you want to do it mapping, do the mapping from the z plane to our w plane, so it will only cover the half of this portion. So first this, right? Because we have this w equal to e raised per iota theta, because the argument will be here, so it will be that theta by 2, right? So that means, so for 0 to 2 pi we have e raised per iota theta by 2. So that means, so it will only cover the first half of this complex plane, semicircle of that complex plane. Now, in order to make the complete transformation from this z to w plane, so that means we need to rotate this twice. So we can then, because here w will go from 0 to pi. So that means if you put that z equal to from 0 to 4 pi, so then w will go from 0 to 2 pi. So what does that mean? So that we are saying that we are basically rotating this angle from this from 0 to pi, then 2 pi to 4 pi. So we are basically making the two copies of this z plane, then we can map it with that w plane. Because if we rotate it from 0 to 4 pi, first from 0 to 2 pi, and then from 2 pi to 4 pi, then we can have this complete, it cover the whole complex plane. It will go then from 0 to 2 pi. So that means we should have two copies of the z plane, then we can map it on this w plane, right? So what does that mean? So that means if we have that infinite complex plane sheet, अगर हमारे पास एक infinite plane sheet होगा, right? So we need two infinite plane sheets. Those are basically called Riemann surfaces. So you need two Riemann surfaces, two infinite plane sheets, and you just put them one above the other, right? So this is how you can define this. So what we need, because we need the two copies of this z plane. So that means two copies, one above the other. Then we can map it on the w plane, because our w is that square root of z, right? So we can have this. So we can have two sheets here. So these will be the two sheets. right? So you need to put these two sheets one above the other, then we can map it to our W plane here, right? So why basically the first what's the branch point? So branch point are saying we are saying that where the two branches basically coincide with each other, where the two branches coincide. So what we'll do, we have two Riemann surfaces and we are joining them at z equal to 0 and z equal to infinity. So that means, so this sheet, so you need to glue it at the z equal to 0 at the origin as well as at z equal to infinity because it is going infinitely. So we have this infinite plane complex, this plane sheet in complex plane. So that means we can have, so we can write that. So that means we need to join them. So the sheets will be like this one. So we can have sheets like this way. So this is basically z equal to 0 and this is equal to z equal to infinity. Right? And these points, one z equal to 0 and z equal to infinity. So these are basically our branch points. So our z equal to 0 and z equal to infinity. Or and so we can, so because we are basically rotating that, if we map that W plane with that, this Z plane with W plane, if we do mapping, right? So that means we are rotating that Z twice, from first from 0 to 2 pi and 2 pi to 4 pi. So then in Z plane we don't know exactly where we are, right? So that means we can write that. So if we join them, so join them at Z equal to 0 and at z equal to infinity. So let me plot it like this. We can rewrite this as, okay. So this will be, so this is our first Riemann surface, first and second sheet. So this is our origin, z equal to 0, z equal to, right? Okay. So these are these Riemann surfaces, and if you rotate it from 0 to 2 pi, so it is going from, so when you rotate it from 0 to 2 pi, right? So 0 to 2 pi, so it is basically in the first sheet. So we have two sheets there. So when you rotate it from 0 to 2 pi, it lies in the first, that Riemann surface, so first that sheet. And when you rotate it from 2 pi to 4 pi, so sorry, 0 to pi. So 0 to pi, it lies on the first plane because, so this was 0 pi, 0 to pi. Now you, if you rotate from pi to 2 pi, so it descends towards the second sheet, right? So that means it descends towards the second sheet, and again to this point, it will again come back to our first sheet, right? So that means there is basically the point where basically the two surfaces, these Riemann surfaces touch each other, right? So those are basically called these branch points, and there are some cuts, or we can say that there are some discontinuities in these two infinite plane sheets, and those are basically called branch cuts, right? So where we don't have continuity, so but at z equal to 0 and z equal to infinity we have continuities, right? So those points are called branch points, and where the cut lies, where the function is discontinuous, we can say that those are called branch cuts, right? And one more point I need to add here. So why do we need these Riemann surfaces? So why do we need these Riemann surfaces instead of simply that complex plane? So first reason is that because in that Riemann surfaces, we can say that on Riemann surfaces we have a single valued function. So we have a single valued function there. So that means at one particular point we can say that it has one value. But instead of that, if you talk about that Z plane, so in Z plane, I'm not sure. I cannot say exactly either I am lying at above that real axis or below the real axis. So that means I cannot distinguish. So if you make comparison between that Riemann surfaces and that simply that complex plane, right? So in Riemann surfaces we have a single valued function. So that means if our function has that square root of that z plus square root of z, so I'm sure that I am above that real axis. But if it has some minus that square root of z, so I'm saying that I'm below that real axis. I'm in the negative quadrant, right? But in that z plane, so if I'm talk about that that plus z square root of z and minus square root of z, so I cannot say whether I'm lying above or below. So this is the main difference. Why do we need these? Because why do we need these these Riemann surfaces? Because so that basically helps us to calculate to see the exact value of the function, to check the value of the function at some particular point. Because in z plane, as I already told you, when you are saying that when you do mapping, so if you remember that, so if you do mapping from this this z plane to w plane, you need to rotate it twice, right? So twice, but we don't know exactly. When we rotate from 0 to 2 pi, we are again reaching to that point, and again when we rotate from 2 pi to 4 pi, we don't know. So actually, our identity loss is lost here because we are rotating twice. We don't know exactly where we are. So this is basically what happens in that z plane. But in w plane, we have this exactly. We can say that whether it is square root of z or minus square root of z. But in w plane, this z plane, we don't know whether our value will be plus square root of z or minus square root of z. So this is one of the main difference between that this z plane, this Riemann surfaces, and that complex plane, right? So in addition to that, so if you want to draw this, so we have this basically we are making transition from this first that infinite plane sheet that Riemann surfaces to the second sheet, and we can also draw it like this. So we can have function like this. So we can plot it like this, right? So this is first sheet, and this is our second sheet, and this is our z equal to 0. Right? So z equal to 0 is our branch point for this, and we can extend that this sheet up to infinity, right? Now I need to add one more point here. By the condition of continuity, I can say that the value of the function at this point is equal to the value of the function at this point. And similarly, the value of the function at this point is equal to the value of the function at this point. So this is by the with the help of that continuity, right? Because the function is continuous. Because this z equal to 0, it connects these two regions, these two plane sheets, right? So that means I can rewrite this as, so I can write that function if we have that, if I plot that function. So this is basically that if you plot that z equal to 0 to z equal to infinity, and if you choose some point here, right? So I'm choosing some, I choose some point which lies at a distance of some epsilon above the real axis, right? And we can write that the function at x plus iota delta in first, that's equal to x with limit delta. Okay. So this is basically so how we can relate these two regions. So this the value of the function at this point should be equal to value of the function at this point, right? But if you talk about that z plane, तो अगर हम z plane में देखेंगे, so it's very difficult to say. So we cannot say whether the value, whether we have that square root of z or minus square root of z. But in that Riemann surface, we are exactly sure that either we are talking about that either it is that plus square root of z or it is minus square root of z. So we have these multi-valued functions. Similarly, if you talk about that, if you have three Riemann surfaces, so that means so what should be the minimum condition for the, so that we should have three these Riemann surfaces. So that means it depends upon the function, what type of function we have. Like we have this square root of z, that is basically this one. So we have this f of z equal to, that's equal to square root of z. So that is z raised power 1 by 2. So that means this 2, that P by Q form. So this side is that how many Riemann surfaces do we need? And similarly, if we have that f of z equal to 1 by 3, so we need 3 Riemann surfaces. So that means we need 3 Riemann surfaces. Sorry. Right? So that means we need 3 Riemann, see these infinite plane sheets in order to see the branch points as well as the branch cuts in that case. And similarly, so that means in that case, so how I can draw this? So how I can connect these regions? So how do I need to? So that means our function first goes, so we can have then 3 sheets, 3 infinite plane sheets there. So the function will be like this. So we can have these 3 plane sheets there. So we can have 3 infinite plane sheets, right? And similarly, what I told in my earlier, so how you can connect these to these Riemann sheets. So you can stick them with the help of this glue at z equal to 0 and z equal to infinity. That corresponds to our that branch points, right? So that means we can have this function like this. So this is our first function. So this is first. So this was second, and this first goes into second, then uh, second goes into that third. Sorry. So we can have this function like this. So second, and this second goes into third, then third goes into this third goes into. So we can draw this diagram how. So this are the z equal to 0, z equal to 0. That's basically our branch point. Or if you want to extend it up to infinity, so we can do that. So that means in general we can say that if I have some function like f of z will be equal to some z raised power 1 by n, right? So that means we need n times n infinite plane sheet Riemann surfaces in order to connect these regions, right? And in addition to that, we have this. Okay, so we have, let's consider we have some, if we have natural log to the some complex function. If we have, like if we have this function like f of z equal to that natural log of z. So this I can write as, so I can rewrite this as ln of r plus iota into theta plus 25. Okay. So this you can write, if you write it in polar form, because you can write that z equal to e raised power or e raised power iota theta, then so you can get this, because we have already discussed these things in our during our classwork, and so this is how you can write that if you want to write the natural log. So that means we can have this function like, if we have this uh, unit circle, so this is r, or this is basically mod of z. So this is ln of z plus iota into theta plus 2n pi. Right, so this is our that natural log of z. So if you put that for n equal to 0, so if you put n equal to 0, we can have that ln of natural log of r plus iota theta, right? So that basically gives us the principal value of that sheet. So that is basically if you put that n equal to 0. So that means if you put n equal to 0 here, so that means that basically gives us the principal value. That gives us the principal value of the sheet, right? So similarly, if we have some functions, so this is basically how we can write that, because if you take the different values of n here, so taking different values of n, you can have that iota, this iota into theta plus 2 pi, putting n equal to 2, n equal to 3. So because n takes values that 0, 1, 2, 3. So by putting different values, so you can have different this thing, right? So that means we have multi-valued functions there, because putting different values of n gives us the different value of this natural log of z, right? So this is basically what is called that multi-valued function, because because n can take different values, right? So you can have different values for this function, so that's why it's called multi-valued, right? And if you right now, if you want to check that, so if I have some function, some exponential function, right? F of z raised power 1 by n, right? Or f of z raised power f of z equals z raised power 1 by 2, and some constant term. So you need to check what will be the branch these points, and what are the branch curves, right? So hopefully we'll discuss in our coming lecture, and we will mainly focus on the problems on this topic.